For what famous constant of nature is Max Planck famous? Answer in the form of a question. Go. Dun, 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 dun. Dun, 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 dun. Dun, 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 dun. What? I'm not going to answer this one. Colleen, what constant am I referring to? Oh, Dan, you're mixed. Hey, Dan Parker.
Hi, I'm trying to fix this. Give me just a second.
Oh no, it's so cool. You look like a space invader. And your face pops through the grass.
Like a chameleon, right?
Dan? Okay, for what famous constant of nature is this man known? Answer in the form of a question. Okay. Am I like that stupid that nobody wants to like be known to associate with me? Is this high school all over again?
Oh, are you asking us a question?
Yes. Yes, I'm trying to ask you a question.
It's on the chat. We put it on the chat. What is Planck's constant?
Oh, excellent. Okay, good. I see. There's the chat. I got it. Alt H. Okay, go. Who was first? Dan Parker looks like he was first. ERB, gonna restart for camera. Sorry for being late. No problem. I was stupidly late too. So, good. Adam Inverson. Oh, in 2 windows. 4, 8, 12, 13. So we need just one more person. Okay. So, Max Planck actually got the Nobel Prize for his, basically he worked out that somehow the energy of a quanta of light is proportional to their frequency, right? And you know that the same constant of proportionality that applies in for light applies to vibrational motion of atoms and molecules. You know, if a molecule, let's say take a hydrogen molecule, and you go from the ground to an excited vibrational motion. You know what the spacing between the levels is on that molecule? Say there's a certain amount of energy associated with the motion of the atoms as they beat back and forth in a hydrogen molecule, right? And that energy is equal to h. The energy spacing between levels is equal to h times the frequency. That's the same h that was in Planck's constant for photons. It applies also to the vibrational motion of molecules. As a matter of fact, that little bugger winds up everywhere in science. You know, H is everywhere. So, I mean, Max, he was just trying to, he was desperate. He was trying to find some way to get the black body radiation spectrum to work, because everybody else had worked it out, and it seemed like that, you know, if you can't quantize it, that the higher frequency should be very abundant, and as you go to higher frequencies, you see more and more light. But and so there's various physical principles involved there. One was the equipartition theorem. And the equipartition theorem says that the energy in a system is going to be equally distributed throughout all the modes of of energy that it can have. So for photon, it's very simple, right? There's there's just one vibrational mode, and so all modes, if they're equally likely, then you get a distribution of frequencies that's very flat, right? And they go to infinite frequency. And so Planck was like trying to figure out why this distribution law worked at low frequencies, but then it didn't work as you start to get to the visible and the ultraviolet and the higher frequencies. And he simply made an accounting decision. Says, well, higher frequencies must cost more. They must be more expensive energetically to create. And then, and using that, he was able to model the black body spectrum of matter. So that breakthrough allowed actually Einstein to revive the particle theory of light. And so Einstein, after Planck published his results, Einstein later, this was in his miracle year, he published one paper, a short paper on the particle nature of light. And Planck didn't actually go there. Despite looking like a madman after after 1901, he didn't actually talk about the quantization of light. He didn't actually talk about the particle nature of light, because people were still really convinced that light was just a classical electromagnetic wave, because the math worked so well for it that way. Applying Maxwell's equations to radiation worked so perfectly that people were basically convinced that that light was a classical wave, right? Then Einstein said, "Okay, hey guys, this is actually in opposition to that." And what Einstein did was he took data from photoelectric effect measurements, where above you can correlate the photoelectron energy to the frequency of light that emits the photoelectron. So, how many of y'all know this story? I'm not getting any answers here.
You're talking about the photoelectric effects?
Yes.
Yeah, it's something about. Yeah, I've heard it, but I don't remember.
Okay. All right. Well, let's go over that real quick then. Come on, light work. It's so crazy now. There's so much good content on YouTube. You guys don't even need me anymore. I'm like a dinosaur, man. I'm obsolete.
That's not true.
Oh my god. Well, thank you. Is that you, Kai? Who said that? Who said that? I have to make a note to give you extra credit later.
Mission accomplished.
Mission accomplished. Okay. So it looks like my document cam may not be working. Let me see if I can get it to work. Let's see. Is it full screen? Camera. I have a very annoying array of different. There we go. I'm going to focus on my wrinkly hand. Oh, come on. There we go. There we go. So can you guys see the piece of paper now? Or are you still seeing the whatchamacallit, the web page?
Only
Still on
Still on
the
blank.
canvas.
Yeah, so he's canvas.
Okay, I'm gonna switch. I'm learning. Let's see. Your screen sharing. New share. Camera. There we go. Okay. Now you see the piece of paper, right? In the hand. Yes. Good. Excellent. So in the photoelectric effect, basically what you have is you have a UV light and a monochromator, and that you shine light onto a metal surface of a specified wavelength, right? So the wavelength is selected at the level of the monochromator, and then you have a metal. Here's a metal of interest. Here's a cathode. I'm sorry, an anode. Right? And the anode can be has a variable stopping potential, and then has a current meter, and then you have some sort of readout. And what happens is that if you irradiate this metal with a certain wavelength, you plot the intensity of light as evident by the photoelectrons. Actually, not the intensity of light, the number of photoelectrons. That's on the y-axis. What you'll see is that for a given wavelength of light, there may be a lot of photoelectrons. And then at a given wavelength, that the intensity of photoelectrons will drop off. Right? And this cutoff here has to do with the metal. Right? And so, for example, for sodium is called a low work function metal. And then you may have, iron, and then maybe you have gold here. And you notice that there's a different cutoff for every metal, right? And the idea is that as the photon comes in, it displaces an electron, and the electron is then collected at the anode, and you can actually measure the kinetic energy of the electron that's emitted from the surface by measuring its stopping potential. Here. This guy up here is called the stopping potential. So basically, what this established was that there's a one-to-one correspondence between electrons and photons. Right? That's basically the photoelectric effect story, right? So, and different metals have different work functions, and so there's a different minimum energy to extract an electron from a different metal. And then once you get enough energy, once a photon possesses enough energy, then there's then there's this one-to-one correspondence between the number of electrons that are emitted and the number of photons that irradiate the surface. Does that make sense? Kind of, sort of, maybe? Okay. So there is something I'm forgetting here about the stopping potential. I forget what I'm forgetting. Does that make sense? But somebody asked a question about this, if it's possible. So here's the wavelength. This will be, go ahead. This is short wavelength, this is long wavelength, right? This might be around 300 nanometers here. This may be around 700 nanometers here or something like that. Does that make sense? So this is really the discovery of the fact that electromagnetism, electromagnetic waves come in, there's a minimum energy that a given electromagnetic wave can have, right? And that the energy of a photon is equal to h times its frequency. Right? And so what this means is that you can't make less energy than that with electromagnetic radiation. It simply doesn't appear in nature, right? And you can't make 1.5 times that amount of energy either. You can either make 1 or 2 or 3 or 4 or 5 or 6 or 7 or 8. You have an integral multiple of h nu in any given stream of particles of light of a given frequency. Right? So these light particles interact then with molecules in a way that is quantum in nature. Right? Let me go to get a new share and go to all right. Now you can see what I've got here on the actually, this is a better explanation for the photoelectric effect, right? Is that when light is incident on a metal, it will emit photoelectrons. And the kinetic energy of the emitted electrons depends on the light frequency and the type of metal. But the kinetic energy of the electrons is independent of the light intensity. That's where this one-to-one correspondence comes in, right? Does that make sense? Yeah. And I'll publish all this. These are my notes from Chem 155, and I know that Kenya has seen them, Pauline has seen them, Calvin has seen them, etc. So this is nothing new for me. But I think it's actually, I didn't really realize the implications of it until recently. Just that light has this minimum energy that it can come in. So, given this, then this is a model of a metal, right? And there's a certain work function. There's a certain Fermi level for electrons in a metal. And if you irradiate with photons of an energy that's too low to excite an electron out of the metal, and you don't observe them, then beyond that, their kinetic energy depends on the light frequency. And the slope of this line, the slope is the kinetic energy, and this is actually derived from the stopping potential of the electrons, versus light frequency. This has a slope of 8. There's Planck's constant, right? It's, I think we know Planck's constant is like 6 digits or something, 6 or 7. So it's one of the limiting factors in how exactly we can know the universe. But I could be wrong about that. But in any case, if you then you can begin to relate photon energies to the energies of states of atoms and molecules, right? So, for example, if you have an atom in the gas phase, and it has only, and this is a fictitious atom, right? Or it could be a very simple atom, but it might have only a ground state and then 2 excited states accessible to the light that you can produce, right? And you'll notice then that this type of energy level diagram will appear because there will only be 2 absorptions of light and then 2 emissions of light. And the absorptions and the emissions will have exactly the same frequency and wavelength, right? So this is a case where for this gas phase atom, this atom that does not interact with its environment at all, and there's no electric field, there's no magnetic field, and it will undergo resonance, absorption, and emission of light at this wavelength and then at this wavelength, right? And let me pose a question to everybody, and you can answer in the chat box if you prefer. Which is longer wavelength, E1 minus E0 or E2 minus E0? Which corresponds to a longer wavelength photon? This transition here or this big one up here? So how do we answer that? We go back to the formula, E equals H nu, right? Yes. Yes, exactly. E1 to E0 is longer. Good. Excellent. Good. So, E1 to E0 is lower. Oh, it's longer wavelength. Okay, great. So now, even atoms have, any atom with p orbitals will have, at every principal quantum level, you say hydrogen, right? It has, it has a Rydberg spectrum. It has a series of converging it has converging series of emission and absorption lines. right? That's for H2, right? For the H atom, it's similar. For the helium atom, it's similar. And the and so in this case, this is probably easier and E1 is large, E1, E2 is smaller. Then there'll be a series of converging lines up above it, right? Now, if you take a similar, you take now, instead of an atom, you take an actual molecule with vibrational energy as well as electronic energy, then what you observe is that in any electronic spectrum that you take, any spectrum with energy that corresponds to, say, the difference between the first excited state and the ground state, you'll see that it's filled with small lines. So especially if you observe this guy in the gas phase. Right? In the gas phase, this will look like a series of very fine lines. Right? And then it will emit, it will absorb in a series of fine lines, it will emit in a series of fine lines. But these will not generally be resonant. Okay? There'll only be one resonant line, and that'll be this first absorption and this last emission. Okay? And the difference here corresponds to the vibrational amplitude of the excited state or of the ground state that's produced after the de-excitation. So, so this is really where we're going to enter into the idea of fluorescence, right? Fluorescence is generally Stokes shifted relative to absorption. And the Stokes shift in fluorescence is equal to the amount of energy lost in the excited state plus the amount of energy deposited into the ground state. So let me just draw you all a fluorescence spectrum real quick. So, for example, oops. Interesting. So, if you look at the electronic spectrum of a fluorescent molecule, you can plot the absorbance or the fluorescence of the molecule on the vertical axis versus wavelength. Right? And the absorption spectrum will oftentimes have ultraviolet peaks, and then it will have a main fluorescent transition that might look something like this, right? So this might be around 300 nanometers. This might be about, say 250. And this guy here, this could be around 600 nanometers. Right? And this is absorbance, right? And if you want to look at the fluorescence, what you'll see is that the fluorescence will have a similar profile, although mirrored into the higher energy range. And this is going to be fluorescence. And this might be, 620, maybe 650 or something. I'm not sure exactly how much Stokes shifting you might expect there, right? But so let's look at an energy level diagram or a molecular energy level diagram that this might correspond to. Now we've got a high energy transition here. I'm going to call this E2, and we've got a lower energy in E1, and then we've got the emission manifold, right? So for the absorption, we have ground state, higher excited state, and then an intermediate excited state, right? So if we put energy into this molecule at a short wavelength there, what that will correspond to is the absorption of energy from E0 past E1 into E2, right? And then the emission of that energy back to E1, right? And actually, the process I just described is probably right around here, right? But what is actually the case is that there are many, many vibrational substates to contend with in each of these two manifolds, right? Or in each of these three manifolds. I'm sorry, actually. There's a third manifold there, so I misspoke. So it's actually possible to have this resonance process here with a longer wavelength photon being both absorbed and emitted in a resonance process. That'll be right around there, right? But what's actually more likely for fluorophore is that it will start here, and any excitation process will take that guy up into the E1 manifold somewhere. And this will undergo non-radiative vibrational relaxation. Right? And then, and this corresponds to an energy loss, right? From the perspective of the photons, that's an energy loss, right? Because we have a high energy photon coming in, then to get the energy back out, we're going to lose some before this relaxes all the way back down into this manifold or all the way back down to here. So now let's think about if we go into the ultraviolet manifold, it will first undergo this vibrational loss, then it'll undergo this. There'll be a second Stokes shift here. This is non-radiated decay here, right? And there's another non-radiated decay. Then there's a relaxation from here into this manifold, right? And then from here, there's a third non-radiated decay. Mm-hmm. So if we excite this molecule using ultraviolet light, we will see, we may see, for example, you could say lambda EX here, and then we may get some light out of this wavelength, lambda EM, this EX for excitation, and EM for emission. Right? And the emission, the H nu EM will be much less than H nu EX, right? And H nu EM minus H nu EX will equal NRD1 plus NRD2 plus NRD3. Does that make sense? So somebody asked me a question about this. Let's see. Calvin has gone off video. He does not want attention. Who wants attention? Pauline, do you want attention? You always want attention. Yeah. Yeah. So ask me something about this crazy diagram.
Well, I was asking what NRD stands for.
Oh, non-radiated decay. Non-radiated decay. So it's basically, it actually happens in just a few picoseconds. So if you excite a molecule into, say, this state here, right? Then the amount of time that it takes to go from this state here to this state here is, femtoseconds to picoseconds. Very, very short. Okay? And that is actually the reason that so many brilliant chemists got shit for careers around my time. Because around that time, all the smartest physical chemists thought, ha, we're going to kick the butt on all these synthetic organic people because we're going to make lasers that tune to specific vibrational frequencies of molecules. And then we're going to excite that mode, and we're going to break specific bonds in molecules, and we're going to promote certain reactions. And a lot of people put a lot of time and energy, invested a lot of capital in that particular fucking type. Does that surprise you? Dan, does that surprise you? Daniel Yoon. Daniel? My cousin is named Daniel.
Oh, really? It's not a common name.
Well, his name is from Daniel, right? But it's spelled DAN apostrophe L. Daniel. That's the way they call him, right?
Pronunciation was pretty spot on, though. Most people they kind of butcher it.
Right. So, if you were a betting man, right, and you're starting your career as an assistant professor at MIT or one of these Ivy League or Berkeley or something like that, right? And you were thinking, I'm gonna be famous, right? I'm gonna do big things, right, in science. And you bet your career on this idea of exciting individual vibrational modes and molecules with an infrared laser, a tunable infrared laser. And you did every goddamn experiment in the book on every molecule you could think of. And it never, ever worked. Never. Except in one case, and that is the exchange of atoms in H2. You can sort of make this work by exciting a mode of vibration in the molecule H2. And you can substitute HD for H2 and stuff like that by blasting it with a laser. But anything more complicated than that, and this strategy fails. Right? And this strategy fails, Carla, because you failed to see that the lifetime of those vibrationally excited states is super short. So as soon as you make them, boom, they're gone. Right? So you make them, all kinds of them. But as soon as you create them, as soon as you excite that mode, it relaxes back down all the way to the nearest ground state. Right? And the heat has gone into the heat bath. It emits infrared photons, emits microwave photons. It dumps the heat into translational modes, into torsional modes, into rotational modes. There's just so many ways to dissipate that heat that this strategy never worked. It's a shame too, because wouldn't it be cool, right? But those experiments never amounted to anything. Right? And it was just like 10 years ago that finally it was a famous physical chemist finally did the HD experiment, and it was like everybody was like, really? That's it? And so the vibrational excited states are A, short, or B, long. And I'm seeing if she's typing it, if she's going to answer with her microphone. Vibrational excited states are A, short, or B, long. Vibrational excited states are short or long lived, right? They have short lifetimes or long lifetimes. Okay. A. Dan Parker says A. Everybody's saying A. What the hell does A mean? Oh, I said A short, B long. Okay, sorry. They're short. Yay. I'm like, hey, what's that mean? Okay. So yeah, so these lifetimes are really short, but they're there, So like when you have a molecule that can access them, and it goes through this. So let's talk briefly then about some crazy things that happen when you can interrogate molecules individually. Okay. Actually, let's start with temperature and solvent. Okay. I'm going to go to a new share here. So let's see. Yes. Okay. So to just berate this subject a little bit more, right? If you have an atom, sodium atom, in the vapor phase, in the gas phase, in which it's not interacting with anything else, no other sodium atoms, it gives these line spectra, right? This is 589. And this is, 589.7. You know, so this is 1 nanometer here. This is about 0.05 nanometers in full width and half mass. So these guys are super, super narrow, right? And these are the simplest spectra that you get. But then if you think about, okay, so now there's a simple atom, then how about a simple molecule? You take a highly symmetric molecule like benzene, right? Now we have a new x-axis in wavelength. This is going from 220 to 340, right? 220 to 320 or something like that, right? And you can see that there are a lot of sharp peaks here, right? So now there are, for benzene, a series of electronic states. 1, 2, 3, 4, 5, 6, 7. Electronic states, you know, maybe this is E1, E2, E3, E4, E5, E6, E7, like that, right? It's going from longer wavelength down to shorter, right? But each of these is complex, right? And they're not like, I mean, this is kind of made up, but they really are complex. They're so complex that if you make this higher resolution, it becomes so complex you cannot even understand it. Period. It just, I mean, like even this little manifold here, there's thousands of bands in there, right? And what you see in each of these is electronic plus vibrational plus rotational structure. Right? And when you throw all those three together, it gets incredibly complex. And in the vapor phase, you can resolve those things. It's possible to do that. Right? The only thing that's really changing is the orientation of the molecule relative to the light polarization that's exciting it, right? And you can average over all those orientations and simulate a spectrum like this, but it's very complicated. And so what we're used to seeing actually is something more like benzene in a solvent, like hexane. I use a acetonitrile in M155, right? Hexane is better to see electronic transitions because hexane is less polar, right? And so here in hexane, you no longer can see the fine structure. And why is that? Why going from vapor to this solution phase, you lose resolution of these vibrational substructures here? What could be happening? Now we're playing 19th century spectroscopy, right? No, 20th century, early 20th century, right? And I'm asking you guys to be smarter than those jerks. No, those people. Those incredibly smart people. Right? So what's happening between the vapor and the condensed phase? So let's pause on that question. And Dan says solvent interactions. Yes, good. Let's hear from somebody else. Dan Parker said that, not Daniel. Dan, not Daniel. Let's see. Do you have any other? Everybody else has a unique name. There's only one Kenya in this class. Can you imagine that? There's only one. Have you ever met another Kenya?
I have.
You have?
Yeah. In the stock room.
In the stock room? That sounds
Yeah,
so
it was like
strange.
a Chem 1B student that came to check something out, and I was like, oh, that's weird.
There's not very many Rogers out there either. I always considered it pretty dorky. And Kenya's pretty cool, all things considered. Roger is like, but so now let's let Dan explain what he means by solid interactions here.
So the solvent interactions, I guess that's sort of obvious. It has to be something about the solvent. But a better answer, I guess, would be it like dampens the interactions. So there's like a broad spectrum instead of each individual peak for the transition. It's kind of similar to like an NMR, where if you have a polar, like an OH or something, will be really broad instead of a nice peak, because it gets spread out over a bunch of different states, I guess.
Mm-hmm. I like it. It's not quite right. I like it. I mean, it's like I mean, I could be wrong too, right? But so this is a particular vibrational mode of a particular electronic state, right, of this molecule, right? And when this molecule is in hexane, right, then there's two things going on. One is that there's, at any point in time, we're averaging over, literally a billion molecules, right? Like that's, probably in the beam path that you're averaging to get the spectrum, there could be a billion molecules, right? 10 to the 18th, So that would be like 10 to the minus 5 moles or something, Or maybe it could be 10 to the 50th, but, like a million billion. It's a lot of molecules, right? The longer time that you spend to integrate that, the more molecules contribute to the signal at any given wavelength, right? So that means that there's actually a broad average, or a long temporal average of the interactions that this molecule can have with solvent. Right? So, at any given point, you could have any one of a million different orientations of the molecule with solvent. Those can change slightly, and they'll change the intensity and the energy and the probability of a given transition a little bit, right? So, there's really two major factors. It's the number of the number of molecules and the number of interactions that that molecule can have with solvent. Right? So this is ensemble averaging, and it was so funny. Actually, I was over at Trader Joe's the other day. This literally happened. I was at Trader Joe's, and I saw a car in the parking lot that said no ensemble averaging on the license plate. I forget exactly how they crunched that into just a few letters, but I was like, oh my God, that's a spectroscopist. He probably works at Stanford, right? And because what they're doing at Stanford, I don't know if they're doing it anymore, but at the time, they were looking at single molecules. So if you can look at the fluorescence from a single molecule, if it's say it's cold, and you can excite it 20 billion times, right? And in the same configuration, it can emit photons from its same excited state 20 billion times. Right? And you can get a spectrum of that molecule in a single configuration. If you can isolate the spectrum of a single molecule, right? It's always a challenge, right? Because the molecule can fall apart while you're irradiating it. You know, when you excite electrons, even a molecule, you are literally weakening the chemical bonds, right? Because for example, it could be pi to pi star type transition, and if you populate the pi star levels, then you weaken the bonds in the molecule, right? And you know, there could be a million reasons why a molecule can photobreathe, but that's one of the things that can happen. So the difference between a single molecule spectrum and an ensemble spectrum here is that the single molecule spectrum, if it's frozen in the condensed phase, it will give you the emission spectrum unique to its configuration, its solvation, right? And that was a kind of a revelation from the experimental side, right? And I'm quite sure that even under those conditions, I could be wrong if I was wrong, but I think that the same rule about the vibrational bath applies. That there's a quick de-excitation in the vibrational manifold, even if it's frozen in the solid state. So going from vapor to solid state, there's a lot of things that happen that change the spectral quality from this complex, modelable spectrum to a mushy-looking average spectrum that you can't model. It has to do with solvent interactions over time and solvent interactions over a number of molecules. Okay? And then as you go to you can go to a more complex molecule, say for example biphenyl, and then it just looks, in hexane it looks completely bizarre, So so all of the above being said, you can still characterize molecules given that basically this type of diagram, an energy versus an energy diagram, basically, that shows the discrete levels that are available to a molecule, right? And here this is a Chem thing, is they use no prime for the ground electronic state, a single prime for the first electronic state, and double prime for the second electronic state. So E0, U1, and E2. So now let's bridge about 10 years of chemical education here. And I'm going to ask you to speculate about what quantum number is changing between E0 and E1, and E1 and E2. Okay? And you might say, Dr. T, what are you talking about? What quantum number? Okay? Let me, Oops. So remember for the hydrogen atom, right? Okay. I'm gonna re-camerify myself here. I don't know if you'll be able to see me, but you're not looking at me anyway, so gosh. Okay, fine, whatever. And so for the hydrogen atom, right, we were able to exactly solve that using quantum mechanics, right? And the only simplifying assumption that we have with the hydrogen atom is that the proton is stationary, right? Right? And when we solve the hydrogen atom under this approximation, we got the following solutions. N, L, M sub L, and M sub S, once Dirac had his shot at things, right? N is called the principal quantum number. L is the azimuthal. M sub L is the magnetic. And M sub S is the spin quantum number. And this is these are the quantum numbers for the hydrogen atom, right? This is a combination of a proton and an electron, right? So now when we go to a big old molecule here, having zero preparation for this, what is changing between E0 and E1? Is it NL, M sub L, or M sub S? Are you guys still there?
Are you talking about A, B, or C?
Any one of them. So there's a so when you go from atoms to molecules, obviously there's vibrational and rotational states that interpose, right? But the same basic quantum numbers apply to the electronic states, right? And going from 0 to 1, we are changing n, right? It's the principal quantum number, and that's where most of this is what these are large steps in energy, right? Now there's also V, and there are actually 3n minus 6 V's, right? For nonlinear molecules, I think. And so there's a whole bunch of vibrational quantum numbers. And then there's also J's, which are rotational quantum numbers, right? This is vibration. And J is rotation. Which mean that these are all, if these are the principal quantum number energy levels, right? These would be for gas phase molecules, and then the rotational levels would be spaced in here like this, right? on every level, there'd be a series of rotational lines, right? And then there are rules for the types of transitions you can make between vibrational and rotational levels. But they're a little bit liberal when you're talking about changing electronic and vibrational levels. Right? And you'll see where I'm going with this. This isn't, I can't talk in like great detail about the physical chemical description of oh shoot. I forgot to wait. I'm sharing the picture of right. Okay, sorry. I wasn't sure what I was sharing. But I'm not trying to describe in great mathematical detail all of these states, right? I'm trying to describe in qualitative detail what these states, how these states might manifest in terms of the spectroscopy of a given molecule, right? So, if you recall, say an infrared spectrum, right? In an infrared spectrum, we might be going up, maybe just crossing these states E0 through E4, right? And there's a twist here with the vibrational states. So these are different. These are most likely different modes. Okay? One could be a symmetric stretching mode. One could be an anti-symmetric stretch. One could be a bend. One could be there's all kinds of different modes that you can describe for molecules, right? And then each of these modes will be broadened rotationally, right? So if you look at the infrared spectrum, right, you'll start and then you'll have a number of peaks, right? And each of these will correspond to a different peak in that vibrational spectrum of the molecule, right? And if you talk about the visible spectrum, right, you might start at a low visible energy. And this could be like, 1,000 nanometers, and this could be like 200 nanometers, right? And you usually start at low frequency and go up. You may see this, right? And then each of these will have a corresponding level in there, right? So this will be an infrared, and this will be a UV vis spectrum, right? Does that make sense? I mean, there's a difference between it being interesting and it making sense, right? I'm not asking if it's interesting because this could be the most boring fucking thing you've ever encountered in your life, in your whole existence. But I'm just kind of curious about whether what I'm saying registers as making sense or not. And it could be that I'm a fucking alien and I don't know how to speak human. I accept that. It could be that I don't know what the fuck I'm talking about. That could be true too. But I am just curious whether what I'm saying makes sense to you. Okay, I got one thumb, I got two thumbs, two upward thumbs. Okay. Good. Justin gave me a thumb. Yes. Ivy gave me a thumb. I love it. Cool. I don't even know how to do that shit. You guys can't see it probably, but there's a little yellow thumb that comes up in front of your picture or your name or whatever. Pauline? Yes, no. Pauline. Talk to me. Say something. Say something, Pauline. Huh? Wait, no, you say it. Everybody's giving me thumbs up now. Except you, Pauline. Don't give me a thumbs up. You have to use your words. Ah! So does this make sense? No? Oh my God, you're in the lab. Pauline's in the lab. Don't get caught. You're actually not supposed to be there.
Oops.
What? Yeah, there's nobody else around. It's not like you're fucking spreading COVID around, but you know the rules. You know them rules. So Pauline will neither issue a yes nor a no to the question, does this make sense? Kenya, does it make sense to you?
I'm just a little bit confused because it says IR and UV vis, so that's the only thing that I'm not sure about. Yeah.
Okay.
Are those two different peaks that you're talking about? Like, you can't see my pointer, obviously.
Well, so for example, these guys down here, these up here, they generally won't be on the same spectrum, right? Because there's different requirements for the instrumentation to access the UV and access the infrared. But you can string them together. You can if you have a good near IR, if there's UV vis, like the UV is up here, right? And then the vis is here, and then the IR would be down there, and then the near IR is here, right? And if you can measure the near IR, then you can get the entire thing in one spectrum, right? And what happens is that first you see these peaks here, right? In the IR, then you see a blank region, right? This would be in the near IR, right? And you don't see any peaks, except for possible overtones of these peaks, but they're generally really weak, right? And then you see a bunch of peaks here, then there's a blank region, and you see a bunch of peaks here. And that's all starting here, right? Starting at the ground, like when the photon has like near zero energy, it'll just be like, trying to excite the molecules through these tiny energies. Right? It'll always start with the molecule down here, and then try to excite it up to these higher levels. Right, Pauline?
Thank you. That makes a lot more sense.
Pauline? Oh, I can't hear you even though you're talking. Ah. Type. Oh, Kenya wrote, oh. Ivy wrote, it's on the bottom of the screen where it says reactions. Okay. Good. Right next to record. Oh, that's where the emoticons are, huh? Got it. Thank you. Okay. So it glitched for a little bit. Okay. Very conveniently glitched when I'm trying to pick on you. Okay. So who likes to be picked on but has not told me yet? I know you like to be picked on. Who else? Carla, do you like to be picked on a little bit? Yeah? No? Okay. So, so if you put in a photon with an energy equal to E0 minus E1, right? If you put in a photon, this molecule, with exactly that much energy, will you see an absorption? if you put in a photon with just this much energy, right, will you observe an absorption?
No.
That
If
was,
you have it,
yeah. Go ahead.
should you be able to see one if you have it like measuring the IR?
Okay, so the infrared frequencies, they're probably going up to about, this is probably this is probably about 4,000 wave numbers. This is maybe 400 down here. Right? And then you get up to here, and you're probably talking about like 1,000 nanometers, right? Nanometers, right? And this is actually 10,000 wave numbers. Does that help? All right. So I realize I've gone over my time again. So the stupid thing on PeopleSoft had us meeting in a room, and it had us going from 6 to 7:40, right? But this is a 3-unit class, not a 4-unit class. So we have to go from 6 to 7:20.
I'm not complaining.
Yeah, well, thank you.
I'm just kidding.
Oh, okay. All right.
I thought you want some reciprocation,
Oh, I do. Believe me, I am all about validation.
Got it.
You need it.
Got it.
Just fake it. I don't care. Just fake it. Just humor me. I will get better, I promise. Every time you validate me, I will prepare more. I'll get more excited. I'll get better. But as long as you treat me like I deserve to be treated, then I'm just going to keep getting worse. So treat me how in a way that will make me get better, not how I deserve. Okay? So on Canvas, you'll see there's a paper called Smiles, right? And you can take a look at the Smiles paper, but I'm in the beginning process of preparing you to understand that paper, right? And it's not really such a long process, right? But I want to get some of these fundamentals understood and like settle down and like completely clear on this so that we can go forward and understand why the Smiles fluorophores are so interesting. Okay. Now I've got to shut up now because I'm not allowed to keep you guys so much longer after our normal time. But think about this a little bit. Email me if you have any questions. And all right. So Adam asks, can we see an absorption that E1 E0? Yes. Well, here E1 is an energy level specific to this molecule, right? And E0 is like the ground state of this molecule. So yes, you can see an absorption, and yes, the absorption does depend on the molecule. So I gotta go. So I will see everybody next Tuesday, same time, same channel, and in the meantime, I'll be slowly putting more papers and stuff up so we can have things to work on, and I'll put some of this stuff up on Canvas as well, along with a recording of this dismal broadcast. All right? Good. Okay. So good night, and I will see you guys next week.
Thanks, Dr. T.
Thank you. Thank you. Bye-bye.
$1 T.
Bye, Albert.
Bye.
Bye, Kenya. Bye, everybody. Bye, Pauline.